Hi, my name is Clayton, and first of all, I would like to thank the organizers for this opportunity to give this talk about my work, which is about C-star polyhedrons in operator algebras. And I would like to start with the motivation behind this definition, which comes from Banach space. In Banach space, we have this definition of polyhedron, which is a family of points, so that every time you take one point of this family, we can separate this point from the remaining one by a closed convex set. So basically it's a family of points, so that every time you select one point of this family, you can separate this point from the others by a closed convex set. That is the classical definition of a polyhedron in Banach space. And this definition, this type of objects called polyhedron, is associated with the geometry of the Banach space. In particular, a polyhedron is associated with some special kind of biorthogonal systems and gives some results about the Weierstrass topology on closed convex sets. To give you an example of this kind of case of these objects, we have this following example. If you take a Banach space which has a biorthogonal system of size kappa, then the support points of the biorthogonal system gives a polyhedron of the same size. In particular, using this result of Markovitch, every separate Banach space has infinite, in this case, countable polyhedron. We know that the density of the Banach space is an upper bound for the size of polyhedrons. So in particular, in the case of separate Banach space, every separate Banach space has an infinite countable polyhedron. But what is the situation in non-separable Banach space? In the case of non-separable Banach space, the situation is a little bit different because, on one hand, if you assume the continuum hypothesis, there is an example of non-separable Banach space without uncountable polyhedrons. This result is due to Kuhn, and also, assuming the mark maximum, a result by Todosevich says that every non-separable Banach space admits an uncountable biorthogonal system. And as we have seen, if you have an uncountable biorthogonal system, we have in particular a polyhedron. The support points of the biorthogonal system give us a polyhedron. In particular, assuming mark maximums, every non-separable Banach space has an uncountable polyhedron. These two results show us that the question whether every non-separable Banach space admits an uncountable polyhedron is undecidable in ZFC. And what we want to do is to have this kind of results in C-star algebras. To this end, we need to look at the definition of polyhedron in Banach space and add some non-commutativity in that definition. And you can do this using some kind of non-commutative version of convex sets. So if A is a unit of C-star algebra, we say that a set is C-star convex if every time we take this point of the sets and now we take points in the algebra, this operation gives an element that is still in the set X, where we assume these points of the algebra satisfy this type of convexity. This definition was formally introduced and studied in the reference tree that I will give in the end of the talk. And we can think about this definition as a non-commutative version of convex sets in Banach space. And some results about convex sets in the classical sense, like results about extreme points, non-commutative version of Rambana, and the Choquet theory, have been generalized using this notion of non-commutative convex sets. Okay, so now we have this non-commutative version of convex sets. Then you can define our object, which is C-star polyhedron. So the definition is exact like the definition of polyhedron in Banach space, but we change convex sets by C-star convex sets. So C-star polyhedron is a family of points in the C-star algebra. so that every time you select one element, you can separate this element from the remaining one by a C-star convex set. And we can ask the same question we did in Banner space. We can ask how big this family of C-star polyhedron can be in a C-star algebra. Again, the density of the C-star algebra is the upper bound for the size of C-star polyhedron. And would you like to see how big it can be, in the sense that if we have a C-star algebra, we have a C-star polyhedron of the same size of the density of the algebra. I separate the results in two cases. One is the commutative case, and the other is in the non-commutative situation. For commutative C-star algebras, so we'll talk about unital commutative C-star algebras, we'll talk about C-star algebras of the form C of K. So the first result tells us that if K is hereditary Lindelof, then the C-star algebra C of K does not have an uncountable C-star polyhedron of projections. We have here a little detail. This zero means that we're actually using this notion of absolute convex sets, this non-commutative version of this notion, but it's a little bit detail. The second result tells that, assuming the continuum hypothesis, there is a non-separable C-star algebra, commutative C-star algebras, without uncountable C-star polyhedron. Actually, this result comes from the same result in Banner space, because it's easy to see that every C-star polyhedron is in particular a polyhedron. So the same example that we use in Banner space, which is of the form C of K, the same examples work in this situation. The last one is assuming the proper enforced axiom, every unit of non-separable commutative C-star algebra of the form C of K, where K is hereditary is non-hereditary Lindelof, has an uncountable C-star polyhedron. These are the summary of our results in commutative C-star algebras. The non-commutative context, we have this result which tells that if you take a Hilbert space and then you take the compact operator on this Hilbert space, then the C-star algebra compact operator does not have an uncountable C-star polyhedron. And in the classical C-star algebra of BL2 does not have an uncountable C-star polyhedron of compact operator, neither it has a C-star polyhedron, uncountable C-star polyhedron of self-adjoint elements. In particular, these results, the first one, tells that if you start with a non-separable Hilbert space, then this C-star algebra does not have an uncountable C-star polyhedron. In particular, we have bigger C-star algebra in the sense of density without uncountable C0 C-star polyhedrons. And to finish here our main reference, all the results is in this preprint, and the others are the main reference we use in your work. Thanks.